Welcome you all to this course on diffraction and imaging. So far in the last few classes, what I was trying to tell you about the different modes of diffraction, correct? That is one using a parallel beam, okay? Another using a divergent beam, and another I mentioned that on a convergent beam we can have this diffraction. So if we consider the parallel beam diffraction, okay, for different type of structures, Bravais lattices, you consider that there are some structure factor consideration, right? What is the basis for the structure factor consideration? Atom position. Other than that, with respect to the beam, one is the beam is parallel, and another is that kinematical condition is the one which is working, right? That means that only one scattering event as the beam passes through undergoes. That's the first thing which we have considered. But what normally happens in a material with electron beam, that is valid only for X-rays. X-ray essentially it is a single scattering mostly, whereas in electron diffraction multiple scattering can take place. We will consider the effect of that later, okay? That will have some effect on this structure factor consideration, okay? And another thing also which we have looked at it is that these extinction rules, we have looked at it for Bravais lattices, correct? Then we have looked for when there is a glide, when there is a screw axis. For those conditions also there are some extinction conditions are there, correct? That I had mentioned and that are given in the table, and also mentioned that for different types of glides, for specific how the intensity of the diffraction spots will be affected. Some spots will become systematically absent. That means that using this kinematical condition of diffraction itself, we can get information about some information about the space group symmetry also, correct? Because when the extinction rules are being followed, it tells about what is the type of a screw axis is present or what is the type of glide is present, which is always related to this symmetry, correct? Then lattice parameter we can determine, correct, from looking at the lattice, but though the lattice parameter is not accurate, okay, from that you get some idea of the unit cell dimension. Then one more information is that when we wanted to find out the complete symmetry of the crystal, only problem which comes in a kinematical condition, okay, is that whether the crystal has got a center of symmetry or not cannot be distinguished, because whether a crystal has got a center of symmetry or not, okay, if we have any reflection one on one, okay, one bar will be also always be present. Whether the atom is there in the crystal structure or not, that is immaterial. This is called as the Friedel law, okay. So that is one condition which is going to be. Because of that, we will not be able to get complete information about all the complete space groups, because in a normal diffraction pattern, what information we will get is essentially what is called as a Lavie group. That is 11 Lavie groups only we will be getting that information, okay. That is the main drawback of that diffraction, okay. This we considered it for a different types of Bravais lattices. Then we know that in the unit cell, atoms can occupy different positions in the lattice, right? Some specific positions different type of an atom can occupy. If atom occupy different type of positions, what is the consequence of that? Atom occupying different positions, the reflections which are not permitted by structure factor rules, they appear as faint and the intensity of the reflection is nothing but, if two atoms are there, A and B, then it will be f of A difference f of B. With some factor it will come. Okay. If two atoms are there in the lattice, two different types of atoms, okay, each has different structure factor, the fundamental reflections are one, where it will be Fa plus Fb, what this amplitude will turn out to be, some factor which will come, correct. Intensity will be squared of this, which some prefactor will come, which depends upon number of atoms which are going to be in the lattice, correct. Is it right? Because FCC it will have, the factor will be 4 will come, right. BCC a factor of 2 will come. Is it not? Because the number of atoms in the unit cell also will come. Is it clear? Suppose a phase transformation takes place, okay, from one structure which is FCC, it goes into a structure which is primitive simple cubic. That simple cubic from FCC to simple cubic. Then what is going to happen essentially is that in the diffraction pattern, which are not allowed by structure factor consideration. For example, suppose if we take a 001 zone, this is how the pattern will appear, right. Correct. This is how the reflections are there. Suppose it goes into an ordered lattice like Ni3Al, then what is going to happen is that, because these are all the positions, this corresponds to 010, this is 100, which are not permitted by structure factor consideration for FCC, correct. When it goes into an ordered lattice, these positions also we will be getting then 110, which is not permitted. In all these positions we will be getting some intensity, okay. But the intensity of these parts will be very small compared to that of this one. This is what I had in one of the assignment, asked you to work out also what will be the order of difference which it will come. That is clear, right. Okay. Then if it is ordered, the lattice is, the sample is completely ordered, this is the sort of a diffraction pattern you will get it. That means that in addition to fundamental reflections, you get superlattice reflection also. Okay. This is a case where the lattice parameter of the disordered lattice and the lattice parameter of the ordered lattice are the same, correct. Suppose it goes from a disordered lattice into an ordered lattice, if it has got a different lattice parameter, then what it will happen? Then it will have a pattern which is corresponding to the ordered lattice with fundamental and superlattice reflections which will be there, which will also appear in the diffraction pattern, correct. Because from the region which we are taking, if it contains both the matrix, that is, suppose that is a, you assume that there is a sample in which a precipitate is also there in this region, okay. This is the beam size which we choose. So, this means that matrix and the precipitate, both of them will give rise to diffraction, correct. Depending upon what sort of orientation relationship exists between the matrix, that is the disordered and the ordered lattice, or you can call it as any a second phase particle, that relationship will be exhibited in the diffraction pattern also, correct. Suppose it, another case which can happen is that these sort of precipitates which are there, these precipitates could be distributed randomly in the sample. Suppose the precipitates are randomly distributed. When we say randomly distributed, what it means? Mathematically what it means? Suppose you have to define, there is no spatial coherence or no correlation, right. Spatially, if you try to correlate from one particle to another, how they are distributed, we find that the distances are random, correct? That is what it can happen. Suppose we consider a case where the second phase particles are correlated in space. The correlation which it can happen is like, you assume that so that means that all have the same size, assume, and all are at some distance. So, this spatial correlation is there, right. Now, what can you think about this one, this distribution now? It is another lattice with a large lattice parameter. Within one lattice, your precipitates form and another lattice, right. Now, I can say that this is what the unit cell of this one. This can always happen. Then how will it be reflected in the diffraction pattern? So, you should get spots which should be inverse of this in the reciprocal space. So, additional reflections will come. Suppose the same particles are randomly distributed, you get only fundamental and superlattice reflections. Suppose you assume that in this particular case, these are about 4 times the distance of the lattice parameter of the matrix. Then how it will be reflected? In addition to it, you will have one will come, some additional reflections will come. This sort of situation occurs quite often. Okay. Okay. Where do you face this sort of a situation, in which type of samples? You give me an example. Other than that, superalize. This sort of periodic lattices which can come. Multi-layer films, exactly. So, multi-layer films, you have a periodicity with which the film repeats itself, correct? There you will be seeing a lattice which is corresponding to each of the sample structure, which is periodic in itself. In addition to it, at a regular interval, the thickness, the film changes from one phase to another phase, correct? There also you will be getting this sort of diffraction patterns. You understand that. Why I am telling is that when you do an analysis, you should know, when you get the diffraction pattern, what are the possible reasons why such a pattern appears. Always it may not happen that you get a very simple pattern. Okay. If a sample is a multi-layer type of a sample, this is the sort of a problem which you will enter. You see, this is gallium arsenide. Okay, aluminium arsenide, it's a superlattice layer, it is being formed. Okay. In this, if you see, this is the way the structure should appear for the gallium arsenide, but you find that there are more reflections which are coming in addition to it. These reflections are coming because it is a multi-layered film, where the thickness of the film is 4 times that of the lattice parameter of that structure. Okay. This is how. This is a high resolution picture, it is all taken from the literature. If you look carefully, there is a slight variation in contrast here is there. Okay. This using another technique called as a C contrast, it could be observed. Okay. That I will talk about it towards the end of the lecture. Okay. Last few lectures I will devote to that modern new techniques of imaging in electron microscopy. Okay. Similarly, here you can see that the silicon molybdenum superlattice structures. You see that here it's silicon and molybdenum layer, which is alternating with a thickness of 50 nanometer thick. And you see the diffraction pattern. If you see, there are very close spots are there. Okay. And the separation between the spots, looking at the diffraction pattern, immediately you can talk about what is going to be the thickness of the multi-layer. So multi-layer thickness could be measured very accurately from the diffraction pattern, because this we also know that whenever we look at a complex like acoustic wave, if you look at it, the wave how it propagates, okay, like when I speak, this can be, when we synthesize it, we go into a frequency spectrum. In a frequency spectrum, it tells clearly what all the frequencies at which the sound is coming, right? Similarly, what we are doing it is that multi-layer, the thickness of the film may be varying from one to the other, small variations will be there, it could always be there. But what all the frequencies with which it gets repeated is in the diffraction pattern, it makes it very clear. So analyzing the diffraction pattern, we can always get information about, okay, lot of information about the structure of the multi-layers, okay. Is it clear? Okay, this is one important aspect. This is all with respect to a parallel beam. You understand that what we are talking about is all with a parallel beam. We are trying to look at a kind of diffraction, and essentially we assume that it is a kinematical condition, so that depending upon the Bravais lattice, okay, we will be getting the extinction, some spots will be not visible, okay. On that basis we can talk about what sort of a crystal structure which the material has, right. Okay. Generally, when the electron beam enters into the sample, we know that electron, since it is charged particle, it interacts very strongly with the sample. What will be the consequence of this strong interaction is that multiple scattering can take place. What we assumed earlier when we derived a formula for diffraction, we assumed that suppose atoms are situated here and a plane wave front, wave is entering into the sample, okay. That is, from every atom position it is getting scattered, okay. It is only that one scattering which we are considering it. So in the case of an electron beam, what will happen is that, suppose you assume that this is the sample and these are all the planes, we know that in the electron diffraction the Bragg angle is very small, okay. Suppose the electron beam enters like this, okay. Then from here it can be scattered in this direction, it should come like this, this is the diffraction, okay. Assume that this angle satisfies the Bragg angle. So this should be the diffracted spot, this should be the spot. Now as it enters here, okay, from here also, as if a scattering takes place, what happens? As if the incident beam is in this direction, a scattering is taking place from here also, right. Now like this, from so many places if it considered, okay, so the spot which this corresponds to it is essentially also acting like another independent source and giving rise to another diffraction pattern, is it not? What will be the consequence of such a diffraction is that, especially in low symmetry elements, okay, the reflections which are not allowed by kinematical conditions, those reflections will become present in the diffraction pattern. An example which we can consider is that this is, I am just drawing with respect to a this is with respect to a diffraction pattern which you get it in titanium, okay. These two reflections, by structure factor consideration, this will be essentially 0001 reflection which are not permitted, okay. Like if this is the direction in which beam is coming, this acts as a center, okay. We have various diffractions are taking place, you have got this pattern. Suppose now this point, the beam coming in this direction, also acts as another one under diffraction takes place. That means that this is the center of the beam, another diffraction pattern will come. Suppose I draw that diffraction pattern, that means that I can write two ways. Okay. That means that now this is the one I had the pattern, but actually the patterns has to are center. If a diffraction pattern comes, you know that this reflection should be present, correct? For this, that means that this is the center also, one reflection has to come here. So where it should be absent, now you find that a reflection comes. Okay. This is a consequence of double diffraction, this is called. This is a consequence of dynamical theory. Okay. Dynamical theory, this is a consequence of multiple scattering for which the kinematical condition is not valid. Okay. Then dynamical theory has to be applied. Okay. That I will come to it later. Maybe after the diffraction is over, we will go into the what the dynamical theory and what all ways in which affects the intensity of the contrast, because that is the one which correctly explains, okay, all the fine structures of the contrast which we observe both in the diffraction as well as in the image. Okay.
This will not lead to Kikuchi diffraction.
No, this doesn't lead to Kikuchi pattern. This is what essentially it is given. Okay. So how to find out that this spot, suppose we suspect that the reflection which is appearing as a faint reflection, it may be there, whether it is a double diffraction or not. What we do essentially is that by rotating perpendicular to, that is, if I take this row, okay, if I rotate the sample perpendicular to around an axis in this one, then what it will happen is that this is the plane, nah? You assume this plane. If this is the axis, around this axis if I rotate, does the plane rotate? The plane rotates, but still with respect to a beam, this giving rise to diffraction. Nah? Then what will happen is that when you rotate, from the symmetry when it changes, these reflections will vanish. Okay, that is one way. There are fine details of it which there is no point in going into this, but I wanted to tell that this is one of the pitfall which happens when other than cubic structures which we go. Cubic structures, what we are fortunate about it is that if you look at the diffraction pattern on a cubic structure like FCC, if we see, so if this is the diffraction pattern, if I take it, this is the spots which appear, correct? If suppose I take this is the diffraction pattern also, the same spot will, the spots will superimpose. That is what it happens. But for low symmetry materials, especially non-primitive one, this we can see it in the case of silicon also. I will just show an example. Okay. I do not know whether the spots are visible. Here what it happens is that if I consider these two spots, one on 1 bar and one on bar 1, okay. If any one of them, if I consider the secondary source, it is equivalent to if I add these two. In any reciprocal lattice section, if we consider it, if we add vector addition of two spots, if we take, the another spot should come. But normally what happens is that when double diffraction takes place, by kinematical condition those spots are not allowed. But when you do it, those spots will appear. That is one way, another way to look at it. Okay? That is what essentially what I have written. That is because what happens in silicon or diamond, if you look along 001 axis, because there is a screw axis along the body diagonal, okay, now we have atoms at 0 position, okay, then at 1/4 position along also atom is there, half position, that is 0 half also plane contains atom, 0, 0, 3 by 4 also atoms are there, then 201 plane comes. That means that 4 planes are there, correct? So the fundamental reflection has to be 0, 0, 4. 0, 0, 2 should become 1 if it is the same type of an atom which repeats, like in the case of carbon or silicon or germanium or tin. In all those cases they should vanish, okay? But by double diffraction spots do appear, okay? When such spots are there, when you index it, you should also know that why such spots have appeared, okay? Along the body diagonal at 1/4, 1/4, 1/4 there is a carbon atom is there. That means that if we look along the 0, 0, 1 direction, that 0th plane is there, then 0, 0, 1/4 there is another plane which contains atom, then at 0, 0, half another plane which is atom is there, then 0, 0, 3 by 4th an atom is there, then one which comes at 0, 0, 1, right? That means 4 planes are there where we have no atoms, right? So now if we look for the reciprocal lattice, if you try to draw it, then the fundamental reflections will come at 0, 0, 4, okay? 0, 0, 2 comes exactly halfway between these two, so that reflection should be absent by selection rule, structure factor rules. But they do appear because of double diffraction. That is, if we take a sample and if the sample is extremely wedge shape of sample, okay, like we have a sample like this and the thickness is very small in this region. If I take a diffraction from in this region and if I take a diffraction from in this region, from this region when I take a diffraction, I may not see the double diffraction. If I take it from this region, the probability of diffraction increases. That is because from this region, whenever a multiple scattering, okay, this also we can consider it in a probability. Suppose a scattering is taking place, an atom from one particular position, you assume the probability for the scattering is P1. As the scattered beam goes further, probability of it to be scattered again is going to be another P1. So what is the probability that twice it gets scattered? P1 into P1, P1 squared it will be, correct? And whereas for one scattering it is P1. So you can see that so intensity, if you take it, it is going to be square of it. So it will get reduced considerably when the thickness of the sample becomes large, the probability of multiple scattering increases. So this is another way you can verify it. That is, if we suspect that there could be a double diffraction, you come close to the edge of the foil and try to look for a diffraction pattern. That way we can identify it, that whether some spots are coming due to double diffraction or not. Is it clear? No, because finally when we do an analysis in a microscope, we should make sure that whatever is the information which we come is the true information. Otherwise, if some spot like this extra spot comes, then the whole analysis of the crystal structure will be some other way we will be looking at it, right? So that should not occur. That's why I am telling you all these things. So this also one has to take it into consideration, okay? What will be the consequence of it, how it affects in the image part of it? When I talk about image, I will talk. But in the diffraction, at least this much one should remember. And now you can imagine various types of cases in your sample as the beam passes through, the way the second phase particles are situated with respect to as the beam passes through, whether there is what sort of correlation it has, spatial correlation it exists. Depending upon that, at least I feel that now you have got an idea that all these things can give rise to extra reflections in the diffraction pattern. Otherwise, you will be thinking that why these spots are coming, correct? Is it clear? Okay. Now, suppose the beam is entering in the sample from here. Then since the thickness is very small, what will be the consequence there? is that essentially the beam is a parallel beam, only a kinematical condition, right? And what is the probability of incoherent scattering taking place? It is very less. Okay, suppose the beam is entering here. What is the probability of incoherent scattering taking place? Is large. That means that this parallel beam give rise to a diffraction pattern which you normally observe like this, correct? That's what you get it. In addition to it, that is if I draw it a magnified view, okay. Okay. At some particular region, okay, you assume that from here an incoherent scattering is taking place. That means that some energy is lost by the incident electron. Then this electron has different energy with which it is coming in all these directions, correct? This is an inelastic, that is incoherently scattered electron, but when these planes are there, it can again coherently get scattered. If it gets coherently scattered, we will be getting a diffraction pattern, correct? That pattern which we get it from this, we call it as a Kikuchi pattern. That is because only the beam which is coming in this direction undergoes scattering. The beam which is traveling in all other directions, they come onto the screen and generate a uniform intensity background, correct? In that uniform intensity background, suddenly you find that in some direction the beam is undergoing diffraction, okay. Those appear as dark lines at the center, and away from it an excess line come, which I have explained in the last class.
So why do you need like a divergent or this could happen in a parallel beam also?
Which one?
This same thing.
Uh,
It could have incoherent scattering even in a parallel beam.
No, the beam is parallel. The incident beam is parallel, the parallel beam is falling onto it. As the beam falls onto it, there are at some positions, okay, the incident electron beam is losing some energy by plasmon scattering. When it loses some energy, has lost that energy, that happens randomly, so there is no correlation from one to the other. Now, in addition to the coherent beam which is coming from different positions in the sample like this, now there are incoherent electron beam is coming. This incoherent electron beam is scattered in all the directions, okay. So, the maximum intensity will be in this direction, and as the angle theta increases, the intensity reduces. So, now we have the same diffraction plane is there which is there for the parallel beam. For some angle theta, this plane satisfies Bragg angle. So, this incoherent is cut. Suppose the sample you assume that it is a amorphous material, then what it will happen is that you will get a overall dark diffuse background will come. That background is going to come even when the sample is crystalline, because intensity is, but only from these regions, okay, the diffraction is taking place. So, in addition to the normal diffraction pattern which you get it like this, okay, you will be getting some patterns which gives rise to.
So, but you said for Kikuchi pattern we need like a divergent or a convergent beam, right?
That is from this point, how is the beam coming?
From that point.
It is a divergent beam, correct? That is what I wanted to tell. Though the parallel beam we are initially putting on that sample, the beam which is responsible for Kikuchi pattern to occur is essentially a divergent beam. You understand that? Emanating from this point. That is what I said. Is this clear? Okay.
So the Kikuchi band and diffraction spot both form in the back focal tube.
Which one?
Kikuchi band and diffraction spot
Yeah.
both form in the back focal plane.
See, what does the lens do? That is, the beam which are all, okay, it's like this. This is a beam which is scattered in this direction. The lens action essentially is the beam, this parallel beam and this parallel beam which is hitting on the lens. This will all be focused to a point. This will all be focused to another point, correct? This is what essentially it happens. Okay. So, all the parallel beams will be focused to the back focal plane. That is as far as the diffraction pattern is concerned. So, but suppose I tilt this sample a little bit here, okay. You know that in the diffraction spots, essentially we have a streaking which is perpendicular to, in this Z direction it is there, depending upon the thickness of the sample. So, the evolved sphere, if we consider it, either it is passing through the spots, and through some of the spots it will be still cutting this streaking. Even if I tilt the sample by 10 degrees, plus minus 5 degree, still some portion of the streaks will be cut by the evolved sphere. So, we get the diffraction pattern. So, diffraction pattern remains stationary, we see it, whereas the inelastic incoherent scattering, the source is within the sample. So, if I tilt the sample, the source also is shifting with the sample. So, because of that, what happens is that the Kikuchi band will shift when we tilt the sample, but the diffraction pattern remains stationary. That is why the tilting of the Kikuchi band is very sensitive to sample tilting. We can utilize this to find out the deviation from Bragg angle, and also we can use that to orient the sample correctly, and the separation between them is very accurate because the Bragg angle is satisfied exactly at this particular point theta value. So, this could be used to find out the lattice parameter very accurately. These are all the three applications of Kikuchi diffraction. Is this clear?
So I think he was asking, do the Kikuchi bands also appear on the back focal plane only?
Yeah, everything.
Not on the final. On the
See, in an imaging when we do, what we do it is that, okay, if I use this back focal plane as the object for the next lens, I will get the diffraction pattern on the screen. If I use the image plane of the sample, then I will be getting the image. Okay, this is the type of ray diagram which you people are familiar with. Okay. Right. This is how it is drawn, right? And these are paraxial ray consideration, only I am drawing it. Okay. This ray which comes like this, okay, this will through the focal point, correct? It will come, and the ray which passes through the chief ray, where these two meet, we have the image, correct? And which is this plane? This plane is the back focal plane, okay. This is the image plane, okay. Suppose I keep a lens here. For this lens, for the distance which is adjusted in such a way that this place becomes the object, then what I will get it? A diffraction pattern on the final screen. Suppose this lens, instead of keeping it here, I can keep it somewhere else here. So, the image is the object. Then what I will get? I will get a magnified view of the image. So, these lenses have to be moved in the case of an optical microscope. in an electron microscope what we do, the lenses are nothing but coils through which we pass the current. If we change the current, the focal length changes. So we don't move the lenses, but we can change the focal length so that the same thing can be affected. This in a microscope what you do, you just press a button, all these things occur. But essentially all these changes are automated in the system. Is it clear? Okay. So far what we have considered is essentially the various types of diffraction, okay, these two. So parallel beam we have considered. In the parallel beam, okay, if incoherent scattering takes place, what will be its effect, which is Kikuchi diffraction, okay. And another thing which is similar to Kikuchi diffraction which has been seen, okay, that's what is essentially in the X-ray diffraction, which is called as a causal pattern. We will come to it now. Okay, this we will come back later. Okay, I just mentioned what all the applications. Applications are precise lattice parameter determination, okay, crystal structure determination, thickness of the foil could be measured accurately, point group and space group could be determined. Okay, I will just give a brief idea about some of these aspects. Especially the point group symmetry and space group symmetry is really a tough part of it, which I will not go into detail, but I will mention. But the others I will just mention. Okay. See, this is just a ray diagram which shows a parallel beam which falls. Like what we have shown here is that all the rays which are parallel to our optic axis are brought to a focal point, right? But if this is the sample, from different points in the sample, there will be a variation in intensity could be there. Na? But still, when they are all focused to a point, you are not able to see any of those variations. That is one drawback of it, but you will be getting just a spot pattern like this, right? This is how we get a diffraction pattern with a parallel beam, okay. Suppose we make the beam convergent. Instead of making the beam, that is we have the lens, okay, I do converge the beam like this, then what will happen? No, this is the sample, I converge the beam onto the top of the sample. Now what will happen? This beam is going to enter into a sample like this. Na? So this is the direction in which the beam will be coming, and if the lens is going to be there, the lens will try to converge it, okay, this, we converge it into this. So what we will be seeing it here is, since the beam is a convergent beam we are putting on the sample, instead of getting a very fine spot, we will be getting a disc. That you can also understand that that beam which is coming like this in this direction, suppose as it enters, it does not satisfy the Bragg condition. This beam will be just coming like this with the full intensity. This beam also will be coming like this with the full intensity. So essentially you will be getting a disc of some uniform intensity, we should get it, correct? If it's a, suppose the material is an amorphous material, that's what it will happen. But if some diffraction takes place or some interaction takes place, depending upon that, some fluctuations in the intensity could occur. Okay. These fluctuations in intensity could be used to get information about point group, space group symmetry, okay. Then lattice parameter determination, strain determination could be done, because in many gamma prime precipitates in material, people have used the precise lattice parameter determination to find out how the strain varies from one region to another in the sample. Okay. A precipitate of 1 micron size, they could map the strain distribution. That is always possible. Okay. Okay. So this is what essentially is being shown. The beam is divergent. Now you can see that this forms, and if something gets diffracted, okay, first order diffraction, this will also form a spot like this. Okay. So now you see that instead of getting a sharp points we are getting a disk, and the disk has got some intensity distributions which are there. Okay. Some lines could be seen, dark lines could be seen, there are so many things which you are seeing it. All these things carry information about crystal structures. Okay. The whole game here is that how to get useful information from this sort of pattern. Okay. Okay. Suppose we make the beam size small, okay, we converge the beam. This is a case where the beam is converged in such a way that angle is very small, okay, so that the spots do not overlap. Okay. And I can change the convergence to a large value, so that if I make the beam more and more convergent, the width of this will increase. So the diffracted spot and the transmitted spot can touch each other, or if the angle is being made very large, then what can they can overlap also. When they do overlap, that sort of pattern is called as Cosel pattern. Okay. This is one technique, this Cosel technique, which is used in X-ray. Okay. Suppose I have a sample here, I put a divergent beam of X-ray here, keep it here, the beam is diverging like this as close as to a sample, then what will happen? Will we get a diffraction? Huh? That is, this is an X-ray source, okay, which is kept very close to a sample, and the beam is divergent, because normally you are used to seeing a parallel beam. What will happen in this case?
Diffraction occurs for some beams.
Diffraction will occur within the sample for planes which satisfy Bragg angle. Others, what it will happen? The beam is coming, and suppose I put a photographic film here, or nowadays you do not use photographic film, you use an image plate. Like for taking our chest X-ray, if you go to a radiologist, they have a film, na? Such a image plate I put it behind it. Then what it will happen is that all the rays, as such it is an amorphous sample, it should be coming and falling on this. Suppose there is a plane which satisfies Bragg condition, then what it will happen is that in this plane, since it satisfies, this is the one region where over the background excess intensity will come. Here there is a reduction in intensity, and the separation is now very large because we are using a divergent beam. So the distance which we can measure is very sharp lines, you get it, and the separation between them can be used to find out lattice parameters. Using this technique, we can find out lattice parameter 1 in 10 to the power of minus 5. It is one of the most accurate technique to find lattice parameters using X-ray. I do not think in a conventional diffractometer you can find up to a fifth decimal place you can find out. Using this technique one can be done. Okay. Exactly that same thing is what is happening in this also, the beam is being made. Okay. Because it is a divergent beam. The beam, though it is converged onto the sample, what happens within the material? From a point it is a divergent monochromatic beam which is coming, correct? So if you look at the spots which are corresponding to it, when the convergent angle is small, we will be getting a pattern like this, and now you see some pattern which corresponds to the first order. Okay. Then if we increase the angle of convergence, here they are almost touching each other, this is the way the convergent diffraction pattern will look like. If we make it all overlap, this is the sort of a pattern. All these type of patterns, various types of patterns are used to find out point group and space group symmetry. Okay. See, here I have taken a case, okay. The same ray diagram which is being shown, it is a beam which is convergent onto a sample. Okay. It is a cone, and the angle of the cone is such that it is larger than the Bragg angle for some planes which are parallel to it. If it is larger than the Bragg angle, what will happen is you will be getting an intensity of the spots. Okay. Then in addition to it, when it satisfies Bragg angle, from that lot of scattering has taken place. So what will happen to the intensity? In the diffracted spot you will be getting a line. In the transmitted spot, now in this ring you will find that there is a reduction in intensity which will happen. Okay. This is exactly like a Kikuchi diffraction. Kikuchi diffraction also, this is what you consider, na? Divergent beam which falls, only a plane satisfies the Bragg condition. Okay. You see this, you look at this one, it is a two beam condition because there is only one plane which is giving rise to. This is the transmitted beam, almost uniform intensity. At the center you have a dark line, and corresponding to it in the diffracted one the intensity is maximum, which corresponds to x. So if you measure this separation, this will tell you exactly what is going to be the lattice parameter. But from the spot, when you see, spots have always some finite thickness, however fine they are focused. So measurement error will be high. Okay. And when I tilt the sample, then what happens is that this diffraction plane is getting tilted. So this spot will also shift. That is exactly what is happening. Okay. But in many of the samples, this is only with respect to one beam which is considered. Okay. Quite often, not only this, we get sort of a fringe pattern which we get it, okay, within the sample. Why this fringe pattern arises? The reason is, I had given an assignment to find out the intensity of the different shape factor, correct? That effect. How does the shape factor, what is the formula for the intensity?
Sin squared.
Yes, tell me. Sin squared pi s into a into n pi s into a it comes, correct? A is nothing but the number of unit cells which are there in the z direction if you take it. So this should become T, right? That can be considered thickness of the sample. What is S into T? So suppose S is the deviation from the Bragg angle. Suppose this S into T, S becomes 0, then what will happen? This term 1, because L-Hospital rule you have to use it. Okay. And this term can be made 0 by two different ways. This product also could be equal to some integer S into T. Is it not? Okay. This S which we considered was a deviation from the Bragg angle. That is, if a finite size of the sample is there, delta k in reciprocal space there is some extension in which the broadening of the peak occurs, and where the first minimum takes place, that is what it corresponds to, that S corresponds to that value. Okay. Just I will jump a little bit, which I will talk about it later, is that this S is in the kinematical condition which consider. In the dynamical theory, this S is written as a factor called as S effective. Okay. S effective is nothing but root of S squared plus 1 by written as psi g squared. Okay. What is psi g? Psi g is nothing but which is called as an extinction distance. Okay. I do not know if you have thought about it, you would have got a feeling for what psi g is, because I said as the sample is very thick. Okay. As the beam enters into the sample, Okay. The intensity, the beam gets scattered in the diffracted beam. Similarly, the primary beam also, like if suppose this is the sample, okay, the beam enters like this, it gets scattered. These are all the planes are there, na? As it comes here, again it gets scattered in this direction, again it gets scattered in this direction, right? When it gets scattered at some distance into the sample, the intensity of the beam will become 0. That distance is, in the crudest way, if we define, that is called as the extinction distance. Okay. That extinction distance depends upon what sort of atom which is going to sit here. Suppose it is aluminum. For the same beam, the scattering of the beam will be poor because the atomic scattering factor is small. Suppose I have uranium here, the scattered intensity will be more. That means that as the atomic number Z increases, the extinction distance psi g will be getting smaller. Okay. Is that clear? Okay. Now let us talk about scattering factor, this one, structure factor. What is structure factor? Structure factor equals two pi I HU plus KV plus LW, you write it, na? If Fa becomes large, what happens? The scattering factor will increase. What does the scattering factor say? It says that how much is going to be the intensity or the amplitude of the scattered wave. So, amplitude of the scattered wave increases if Fa increases. That means that Fa, the atomic that is the structure factor and extinction distance are inversely related. You understand that? What exactly relation we will come later, but now you have got some idea of that. If the structure factor is going to be high, then the more scattering will take place as the beam enters. So, psi g will be small. So, they are inverse relationship. This much is clear? Okay. In fact, I can write it in a very simple form, that this psi equals, okay, structure factor into, I put it as a, I will put as Fa into shape factor, right. This structure factor I can write it as equivalent to 1 by psi g, some other constant terms will come proportional to structure factor. This way also I can write it. That is what essentially will happen. This you will see it later. Okay. You understand this, what this psi g is? That means that if I use the dynamical theory consideration and instead of S write as S effective, this term will become S squared plus 1 by psi g squared into T squared should be equal to some integer n squared, na? For which the intensities will become reduced. That means that either if the thickness varies or if the no, not the extinction distance, if the deviation from the Bragg condition varies, both the effect will be to give rise to some fringe, that black and white fringe has to come. So, these fringe which it comes is because here when the beam enters, this satisfies when this plane satisfies the Bragg condition, there S equals 0, correct, because perfect Bragg condition is being satisfied, and all other ones, though the beam is all falling onto the same region, but it is with different S. So, that will give rise to a fringe pattern. This is the fringe pattern which you get it. In fact, this equation, if you know the material which it is there, if you know psi g, okay, this expression could be used to find out the thickness of the file. This is what it is being done. That is looking at a fringe pattern like this, finding out what is the, if you know the lattice parameter and this distance, I am only just, this is the formula which is used, okay. And there are ways to do it. I am not going into a detail which you can see it from this, you can study it later. Essentially, if you try to plot, okay, Si squared by Nk squared, because this is only the mathematical jugglery which we are trying to do it, okay, versus 1 by t squared, the slope of it will be 1 by t squared, from which the thickness of the file could be determined. Because for many applications, suppose I wanted to find out the dislocation density in a sample, what I should do? To find out the dislocation density, if I have to do it, I can see the dislocation how they are distributed. But if I do not know the thickness of the sample, how will I find out? Because we should know the volume of the sample. Nah? Because the area where the beam has fallen, that defines the area. But unless we know the thickness, so many applications we require the thickness of the sample accurately. This technique could be used to find out the thickness of the sample. Okay. Is this clear? So, the basic philosophy is just how the S when it changes, because this expression, when you are familiar with it, this is what the intensity it gives it. But depending upon the variation of S or T, similarly, suppose S remains that same, okay. If the thickness of the sample changes, like suppose we have a wedge shaped sample, okay. The beam is falling at some particular angle, but with respect to the diffraction plane, it is satisfying some value of S. But the thickness of the sample is changing now. As the thickness of the sample changes, what it will happen is that you will be again getting a fringe contrast. This I will come to later and show you some examples where you can see fringes near the edge of the sample. All samples invariably you will be seeing it, okay. That is because of this effect. That is all coming from this expression of the intensity. Okay. In fact, a similar form of expression only will come after dynamical theory also. But some of the terms, like I just have told you that instead of S, this is the way that will come. These are all some modifications which will come in those expressions. Okay. Now, and another effect which it can happen is that whenever a beam enters onto the sample, okay, the evolved sphere, whichever that spots which it cuts, those are all the only spots which will be see as a diffraction pattern. Correct? Na? Okay. Suppose I make the camera length very small, that is distance from the sample to the screen very small, then what is going to happen is that in the same area, instead of only the central spots which are enlarged, now because you can see that some of these spots are also being cut by the evolved sphere, they will also appear. So, this is the zeroth. So, the one which corresponds to these spots correspond to the zeroth order Lave zone, or for which we write HU plus KV plus LW equals 0. Okay. This is also nothing but what we have written when we started the class itself, equals plus minus n. This is all the various interpretations of this expression only. Okay. When n becomes 1, then this is the first order, n becomes 2, it is the second order. That is nothing but the reciprocal lattice which you have constructed for a simple cubic structure itself, R and FCC. If the beam is falling along 001 direction, if you see the plane which corresponds to the passing through the origin, that is the where it will be satisfying the zeroth order Lave zone condition. Okay. The one which is the next plane, like this plane, it will correspond to the first order, the next one will be the second order, like that it will happen. So, when we reduce the camera constant, we can get first order planes also, and if we index these, and then try to superimpose onto it, then looking at that structure we can find out what is the type of a Bravais lattice. All this information we can get it. Okay. That means that essentially in one diffraction pattern we have got the full reciprocal lattice, spots corresponding to a full reciprocal lattice part is already come. Is this clear?
Superimposing means what?
Superimposing means that because since only these touch, we have got these spots. Na? Suppose we know this is the separation between them. Now I can extrapolate it by putting the spots at regular intervals, this distance it has to come, which they are not appearing it because they do not satisfy the Bragg condition. If I do it right at the center, I will be getting the spot which is corresponding to it. Suppose the central one corresponds to, with respect to a reciprocal lattice which you have constructed the unit cell, the first plane, the one which comes above that will be corresponding to the next plane correspond. That way you will be able to do that. Na? That is how you do the analysis. Is it clear? Okay. So that is what I am showing it here. How to, and in a Kikuchi diffraction, what happens? We are making the beam little bit convergent. That means that it is not a one oval sphere. Corresponding to each direction, you can have a series of this one. So over a range of value, okay, in which it covers. So first 0th order, first order, second order, all the spots we could get it. Okay. But generally what happens is that to get all these spots, it is not that easy. Okay. Because as we go to higher order diffraction which are taking place, the vibrations of the sample will come into play. Atomic thermal vibrations will come into play. In such cases, what is normally done is that when you wanted to get second order, third order and all, you cool the sample to liquid nitrogen temperature, then this vibration, thermal vibrations will get reduced, then we will be able to get a sharp pattern. Okay, here if you see, this is 0th order, this is the first order and this is the second order. Okay. And another thing which you can see it is, if you see here, okay, this is a, we know the evolved sphere radius, right. If we can measure this distance, because from this part to the center if I measure, I get this distance. Na? So where this the ring cuts, that distance I can get it. Okay. And this is nothing but a what is it? It's a chord. So for the chord, the length of the chord we can find out, okay, from the geometry. All these things you have studied. So that means that if the length of the chord you can find out, then you can find out from here to here what this distance is. That means that from this one to this one, at what height it is going to occur, you have got that information. And then these parts, if you have indexed it, the unit cell in this direction, suppose we take a high symmetry zone axis, if we get it, take the diffraction pattern. So then we have got A and B parameter here, and measuring this distance we can find out the C parameter. So the unit cell parameter could be obtained from this pattern itself. Is it clear? So from this one diffraction pattern, the full unit cell parameter we can get it. Is it clear? Okay. This is all the expressions which are given, that you can read it. Okay. So here what I have shown is a simple thing, like for an FCC, for the 0th order diffraction pattern, this is what how the diffraction pattern looks like for a 001 zone, the 00, 20, 20, 200. The reciprocal lattice section corresponding to the first order Labé zone if I take it. Okay. No, this is corresponding to for the 001 zone, this is for 110, this is 111 type, and this one corresponds to the first order Labé zone, how the spots will come. Okay. If I superimpose these two, I will be getting how with the first and this one how they should appear, correct? That is exactly what is it being shown here. So this is how, this for a face centered. In a primitive what it will happen is that this will coincide here, this is the way the pattern will appear when the 0th order and the first order are overlapping. All these things you look carefully, then you will understand. These are all very simple things, two patterns which are being superimposed one on top of the other. Okay. And once this pattern is analyzed, we have the full information about the reciprocal lattice. If you have the information about the reciprocal lattice, about the corresponding Bravais lattice, you can get that information. Okay. And this is what exactly it is being shown. This is how the diffraction pattern looks like, what you get it. And then when you know this distance, you create a lattice of this type and just overall expand it and superimpose it. Then you can make out that this is for a primitive lattice. So when you superimpose it, this is how the pattern should appear. If it is a face centered cubic lattice, this is how it will appear in the diffraction pattern which we get it. When we do a superimposition, this is how it appears. Body centered lattice, this is how a pattern will appear for a 001 zone. When you superimpose it, it happens. This is for this is B centered, this is the body centered. Okay. Like this, these are all generated patterns. Then you can compare it with it and match it and measure it. That way you can do the analysis. This way we can identify, okay, the crystal structure. You understand that? Okay. What I will do it is I will stop here. In the next class we will take it and complete this.